Good afternoon. Good afternoon. All right. I think that means hello and hello. Okay, wait, I'm going to start this. Wait. Okay, yes. Or wait, no, actually. Okay. Right. Good afternoon, Isabella. Hello, Rachel. Good afternoon, Farina. Hello, Amanda. Hello, Elias Dorian. Hello. What? There was more. Sorry. I think that's. Why can't I do this? How many years will it take? Maybe all this entire virus and everything was invented just to force me to learn how to Zoom properly. Maybe we only need like 3 more years of this virus just so I will actually become Oh, hello, Amanda, if I didn't say that. And good afternoon, Farina. And hello, Rachel. And good afternoon, Isabella. And hello, Elijah Asdurian. I'm now going backwards because that's what I'm doing. Okay. And as other people, and hello, Viola. Hello, Tania. Okay. We are going to get rolling. Okay. So I do understand that we're almost there. I knew we were almost there, but we're even less almost there or more almost there than I thought. That is, okay, so we have today. We have Wednesday. We have a week from today, and that is it for our classes. Then begins final exam period. So as we mentioned before, your final exam will be posted like either next Monday night or next Tuesday, and then you'll have till 11:59 p.m. Tuesday the 25th to do it. By tomorrow or by this Wednesday, I will put a document in your stream which will, let's not even call it the practice exam anymore. We'll call it the rough draft of the final exam. Like I will have a document in your boxes by Wednesday, which will essentially be what your final exam will essentially be, subject to minor updates or revisions or corrections or things that will be done just to make it more clear or more applicable to you. It won't get harder. It won't get longer than whatever you see. It just might get tighter or clearer. And we will spend Wednesday and or Monday of next week actually talking about the document that will be your final exam. So we're going to try to wrap up this whole course by doing that way, if that makes sense. And that means I'll either be giving you solutions or whatever. I don't literally solve for you right in class. You'll know what you exactly have to do for the final. Anyway, so that'll be more clear on Wednesday. But as we've said, I think a number of times, a big bulk of your final exam will be solving these various cases of Doppler effect problems. So for good or for bad, it's been emphasized so much, we're going to continue to emphasize it and continue to expect that you can. So that's what I'm going to try to today really highlight. I'm going to really try to today to admit more people into the room from the waiting room. Today, I'm really going to highlight or try to highlight exactly what it is about the Doppler effect that I really want to test you on or have you explore on the final exam. Hold on, let me just change the lighting. Sorry. Right. Okay. So, right. Okay. So we're still in Doppler effect here for anybody who's joining us now. And I'm still, for better or for worse, the packet of notes that I'm dealing with. More people coming. The packet of notes that I'm using here is the same packet I've been using for 2 weeks. I'm just adding pages to it in various places for good or for bad. So, and I'll just keep putting the PDF in your boxes. But so so in my view of the Doppler effect, there's four basic permutations or four basic cases that could be analyzed. And yes, first and foremost, your responsibility on the final exam or in life to me is to be able to do the computations, to get the numbers. So first and foremost, if I give you the basic setup and basic numbers, setting up a situation, you should be familiar, you should not be surprised to know that more people are entering the room. You should not be surprised or thrown if I refer to any or all of the four cases. And I don't care, more people could. I can't even, I don't care about whether you call it case 1 or case 2 or case 3. Like I'm trying to be consistent about which one I call case 1 and case 2, but even I think I'm perpetually failing at that. I don't care about whether they're called case 1 or case 2, case 3. What I care about is the four different cases. And again, in English, what I mean by that is receiver approach or receiver recede, source approach or source recede. Okay. And if I'm ever talking about four cases, I'm assuming in my mind that I'm keeping the numbers the same for all the four cases. I'm just that the only fact I'm changing from one case to the other is the direction of motion and the object moving. So really, this is like a compare contrast kind of deal. And yes, first and foremost, you should be able to crunch the numbers. And if I were really a good person, perhaps I would just like set up a chart right here for you with the numbers and with all the resulting numbers for this one particular numerical example that we keep doing. Apparently, I'm not that good of a person. You might want to do that for yourself. I am claiming that with one procedure, you should be able to solve any one of these cases. But if you follow that procedure carefully and correctly, you shouldn't have to memorize anything. You should be able to logically apply that procedure. And yet, what you'll find is that you get a different answer for each of these four cases. And it's that compare and contrast. And you should have an intuition for each one of those answers. Like if I just made up a new number, which of course I would on the final exam, if I just, even if we're talking about sound that still is moving at 340 meters per second relative to the air, if you should get familiar enough with this that if I said that the frequency of the sound as measured by the source is 256 hertz, which is a middle C, rather than the 440 hertz that I keep just like pounding in here. Like I'm just using one example over and over again to try to make this clear, but of course you should be able to do any example. And so if I make an example where the frequency as measured by the source is 256 hertz, and if I say, oh, and the receiver is moving through the air at 95 meters per second, that shouldn't throw you. You should still be able to do the logic of each case. And and what I was trying to say is hopefully, if you get familiar enough with this, you should be able to anticipate what the answers are roughly going to look like, not know the answers exactly. I don't know the answers exactly if I just make up a new problem, but I have a sense of each answer, whether it should be bigger than this one or smaller than that one, whether it should be bigger than the source frequency or smaller, et cetera, et cetera. So you want to develop an intuition for that. And again, that's what we're going to sort of investigate today. But one main punchline, and by the way, we're doing this, there's a part of me it's not meant to be that hard. You notice that even though we're doing this and doing this again, you don't have to do all this calculus and stuff in order to get these answers. We had to do all this really hard, intense calculus in order to believe that the reasons for why this effect is true. But once we had to be able to, I think, conceptualize those beliefs, but once we've actually done all this calculus to derive the reality of a Doppler effect, then the Doppler effect is actually straightforward algebra. Like there's not a lot of math to do here. There's not even a lot of details to manage. They're just enough to make it something, but it's not meant to be a crazy thing. It is, however, meant to be something that is very rich in conceptual content. There's reasons that I care about this so much. Hopefully you will see many of those reasons in our last 3 days by the time we end. But I think it should be approachable by all of us. So, okay. So what I'm saying right now that we're going to see today is we've got these 4 cases. Right now, we're doing those 4 cases through the lens of one numerical example that we've been pounding in for days and days. In the one numerical example, I'll turn the page in a minute and you'll see, but in the one numerical example, we happen to be emitting a frequency which, as measured by the source, is 440 hertz. We happen to be talking about sound, which travels at 340 meters per second through air. And we happen to be talking about a situation where one of the objects in question, either the source or the receiver, is moving through the air at 40 meters per second. Like, those are the numbers on the table right now, just for clarity. They are sort of arbitrary, but sort of realistic. And the one thing I want you to, and I think we've gotten some answers for them. We'll review those answers again in a second. But the first thing I want you to see, kind of the reason we're testing on this and making such a big deal, is I want you to see that when you hold all the numbers the same, and you look at what we're generally calling case 1, when you look at the situation that the receiver is approaching the source at 40 meters per second relative to the air, we get one frequency shift. Like, oh yeah, there we go. Like, instead of getting, well, all right. The first thing I want you to see, I'm going to turn the page again in a moment so that you can see the numbers. But conceptually, the first thing I really want you to see is when the receiver approaches, we get one Doppler effect result. Like, instead of getting a frequency of 440, we get something like 492 hertz. But if the source approaches, and again, all numbers being kept the same, if the source approaches, we not only don't get 440 hertz again, but we also don't get 492 for the frequency as measured by the receiver. Like, either case, we get a Doppler shift. In either case, we get a result that says that the receiver does not measure the same frequency as the source, i.e., in either case, the source sends out a 440 hertz sound, a middle A on the piano, and in both cases, the receiver will not receive a 440 hertz sound. However, in one case, when the receiver is coming in, we get something like 492. And in the other case, when the source is coming in, we get something more like 499. Not a huge difference, but just big enough to be bigger than a difference in rounding. I mean, that's like, it's not just a calculator error or like a digit expansion kind of issue. It actually is a difference. And to try to be more clear, if the kind of speed we were talking about was even bigger than 40 meters per second, as it probably will be on the final exam, just to make this even more vivid, if instead of talking about 40 meters per second, we were talking about like 80 meters per second or 150 meters per second, or anything even up to 340 meters per second, like, which is all possible, the higher speed we're talking about, the more of a dramatic difference we would see. And you, sorry. Totally, yes. Wait, so good question in the, yes, I think I could. So, question in private chat, does this have to do with the wavelength and direction? And the answer is yes. I think I'm going to show that even, I'm going to expand on that even more, I think, as I'm talking, but yes, like, good question and good answer, if I'm understanding it correctly. Well, here, let me show you the numbers that I'm talking about. Right, okay. So, like, what's on the board right now is, I believe, an example of the numbers that we've been dealing with, right? And what's on the board right there, like, what's in black is, in a sense, case 1, you could say, and what's in blue is what I often call case 3, or maybe sometimes I accidentally call it case 2, but it's a different case. It's all the same numbers, but notice the assignment of the numbers is slightly different. So in the black, what we have is the receiver moving through the medium at what I'm calling their -40. Why do I say negative? Because if I set up my coordinate system, as I always do strategically, if I stick with the strategic choice to set up a coordinate system such that the velocity of the wave is always called positive, like, if I want to keep my life And again, we have to make some kind of choice. We have to assign a coordinate system always in physics. We can make any choice we want as long as we're consistent with it, but we probably want to make a choice that is as convenient as possible. So I always set up my coordinate system so that the velocity of sound relative to air is positive 340, not negative. Like I could make it negative, but then I'm gonna have a lot of negative signs and a lot of like counterintuitive things to keep track of. And it would work out, but a lot more difficultly. So I set things up so that the wave is going at positive 340. And if I do that, then if I have a receiver coming in toward the wave, I would call that negative 40, right? So that's the case in black where the receiver, let me just write, sorry. Okay, so the two case, so whether you call it case 1 and case 3 or case 1 and case 2 or blah, 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 what's on the page right here is a compare contrast of two cases where all the numbers are similar, but I'm just shifting around the physics picture. The black picture is, I mean, the picture in black ink is the receiver going, I'm sorry, the receiver coming in at 40 meters per second, negative because it's going in the opposite direction that the wave is traveling. The case in blue is, oh God, no, I don't mean to write, I do this every time, sorry. The case in blue is, I did do the numbers right, I just said it wrong in English. The case in blue, I do this every time, is, and Eli Astorian knows that. Okay, the case in blue is instead of the receiver coming in, it's the source coming in, right? Either way, it's approach. Either way, it's something coming in. But if you think through the signs or the coordinate system, like when the source is coming in, then I'm saying it's going at positive 40 because it's going the same direction as the wave, right? Right. And you know, so if you compare those two cases, what I'm claiming is, I mean, and hopefully we've practiced, you hopefully have practiced this during class time. Hopefully you've practiced this during lab. Hopefully you've practiced this outside of class time. But if you just run the numbers, if you do the exact same procedure for both these cases, what you find, I think I have it on the next page. Yeah, what you find is that, I mean, there's a Doppler effect in both cases, and there's a Doppler effect in what I would call the expected direction in both cases. Like in both cases, what the receiver measures for this frequency is not 440, right? The source sent out a 440. The receiver gets something that's other than a 440. And the receiver in both cases gets something that is higher than 440. That I think should not surprise you. I think you, by the time you take the final exam, you should know that even before you run the numbers that would happen, because in both cases, like things are squeezing together. In either case, like either the receiver's running into the waves, like you standing at the beach, like you at the beach at Coney Island, like running toward water crests, right? Or it's a boat that's making the waves running toward the, driving to, moving toward the shore while it makes waves. Either way, there's like a squeeze between source and receiver. And I think it stands to reasoning, or it stands to a mental picture, that in either case, the waves are going to hit the receiver more often than they're sent out by the source, right? And again, like in both cases, we get a Doppler shift, a Doppler effect, which yields a received frequency higher than the source frequency. Again, here in both these cases, the source frequency was 440 hertz. We get something higher than that according to the receiver in both these cases. However, what I really want you to notice, one of the main thrusts of all of this is, once you get used to running the numbers, you find even though we get a received frequency that's higher than the source frequency, we don't get the same received frequency in both of these cases, right? We don't. And that is interesting. That is worth stopping on. That's worth asking you a bajillion questions about if we wanted to on the final exam. Like, this is worth analysis. The analysis is only going to make sense if you first know how to run the numbers on your own. This is all just abstract unless you can just do the computations first and see the numbers that I'm talking about. In this case, in other words, running the computations is almost like running the experiment and getting data. Like you have to do that to even know what I'm talking about. And even ideally, you have to do it enough times that you start to make predictions and start expecting what kind of numbers you'd get when you run the numbers. But assuming you've done that a bit, now observe with me that in this case, we get one result, but in this case, we get a different result. And similarly, if we look at the two receding cases, like if we have the source moving away versus the receiver moving away, we'll get two numbers that are like in the same ballpark, but are not actually the same number. Now I think I pointed this out right at the end of last class, but this is what I want to talk about right now. That is a very interesting, to me, a very interesting observation, and it has implications. So if nothing else, you should be please checking your notes or either checking my lecture notes from last time or check your own. Please make sure that you also have numbers like this and you know what I'm talking about. Like where I wrote 494, you might have a number like 492, that's fine. Where I wrote 500, you might have a number like 499, that's fine. I mean, there is some rounding going on and some digit chopping, but not enough to account for this difference here, this distinction that I'm saying. So please stop me if you don't know what I'm talking about, or if you don't see these numbers in your notes or in your head. But what I want to say about them then, assuming that you are okay with these numbers, and by the way, anybody who wants can also just put in the private chat, like, yes, confirmed, like, yes, I know what it might even help me. But oh yeah, and similar, oh, thank you. I totally appreciate it. That makes me feel so warm and fuzzy. Thank you, private chat person. Okay, that's 1,000 million karmic points. And thank you, Elijah Historian, also. Okay, he's a famous jazz pianist. You can look him up. Okay, but also a chess player. But okay, oh, also, if you really are following this, or you are trying to practice for the final exam, you might just for clarity's sake, if you're practicing with the other two cases, because the other two cases work the same concept. I'm like trying to focus heavily on just one particular compare and contrast to make the point. But if you're following me, you'll also find that with the two receding cases, like when the receiver goes away, you get a number that's lower than 440. You get something like 386. But if the source moves away, you also get a number that's lower than 440, but you don't get exactly the same number as when the source moves away. You'll get a number more like 391, and you might get 393. That's also, it sort of depends like when you chop the digits and where in your calculator. But if you get like 391 or 393 for source recedes, you're not crazy. And if you get like 386 or thereabouts for receiver recedes, you're good. And what I want to say is this is actually like a thing that these numbers, like, honestly, what I really want to say is if I've been doing everything that I should in physics to this point, if I've been listening to not only physics in general, but the very physics that drives this phenomenon, I really would have expected, if anybody asked me to predict, and maybe Wu did ask you, I mean, we used to when we weren't in COVID, if anybody asked me to predict, if I had solved for case one, if I had solved, probably go back to if I had solved on my own for this, I mean, like you guys did, like last week, and then someone asked me to predict what I would get for the other case when instead of the receiver approaching, when the source is approaching, I would totally predict that I get the same number. I would have predicted that I get 494 for both of those cases. And I'm saying I would have, not just as a person with intuition, but a person with physics intuition, right? If I've been listening to all the physics we've been doing, I might have predicted that I get the same number for both. And what I'm doing here, why I'm taking so long with this, is I almost want to convince you all first that you should have predicted that. But then I want to convince you that that prediction is wrong. So that's like a little bit of a weird task on my part. But if any of you at any moment even had a flashing thought for one moment, like, wait, shouldn't those two be the same answer? If you even thought that for 1 second, then you are not crazy. And in fact, that's very good. If you even thought you thought that for 1 second, and then if it just got pounded out of your mind because you saw that the numbers didn't work that way, or because I was saying something else, like go back to that moment for a second in your mind. There's a reason, a very good reason, that you might expect the receiver approach case and the source approach case to get the same Doppler effect result. That would be a reasonable expectation Yet it isn't the case. This is what I'm here to discuss. So let me be more clear about that, or let me try. Remember, I know I've written these down a bajillion times, but let me just refresh you. The Doppler effect, like when you work out the numbers, you're using only two equations and you're using them over and over again. Well, I mean, you're using two concepts and you're using them over and over again. You're using this over and over again. And in effect, well, you're really using all these, but you're using like this over and over again, right? In other words, and if you switch this around in your mind, what you're really saying when we do the Doppler effect, the Doppler effect is only happening. Well, conceptually, remember the Doppler effect is that a source sends a wave to a receiver, and if the source and the receiver are in two different reference frames, that is, if they're moving at two different velocities, then they will measure two different frequencies. And we're saying that both of those frequency measurements are equally legitimate. Like one is correct in one frame of reference, the other is correct in the other frame of reference, and neither frame of reference is more correct than the other. They're both right, because in effect, what we're saying is frequency is relative. The frequency you get depends on what reference frame you're in. And we're saying, in effect, the laws of physics are the same in all different reference frames. And all different reference frames are therefore equally, or all different inertial, unaccelerated reference frames are equally legitimate. So the Doppler effect right from the get-go is being driven by this premise that velocity is a relation between two objects, not a property of one object, right? Like even by saying you can get one frequency measurement and I can get another and they can both be right, that's already like a very relativistic, a very relational kind of thing to say, that we would be surprised by for a scientist to say, like, you can get one answer and I can get another and we're both right. Like it doesn't sound like science at all in some ways, unless you really have gotten used to the fact that the physics branch of science, a lot of quantities are very much that way. Specifically, particularly velocity is very much that kind of quantity, that you can't actually talk about velocity any other way. Just a last reminder, I know it's come back to this all the time, but like how fast is the earth traveling? Well, it's traveling, or how fast am I traveling right now? Well, I'm traveling 0 miles an hour relative to the earth, but I'm traveling 65,000 miles an hour relative to the sun. And I'm traveling 650,000 miles an hour relative to the galactic center. And each one of those velocity measurements is equally valid, because what isn't valid ever is to say in physics, I am traveling this fast, end of discussion. I am traveling 0 miles an hour in absolute space in the universe. I am objectively traveling 0 miles an hour. That is my speed, regardless of who is looking, regardless of what you compare me to. Like, that's insane. Not just because I'm using an insane voice. Like, that is not how velocity works, right? And apparently that's not how frequency works, because frequency is tied to velocity. We are totally saying that the Doppler effect is the effect of the relativity of velocities, but in the special case of waves, right? So the Doppler effect is like two concepts being combined at once. One, the relativity of velocities. Two, the nature of waves, specifically that waves travel at a certain speed relative to their medium, and then have frequencies and wavelengths that adjust according to that. Now, why am I saying all this? Why am I saying all this? Well, if you really get that, if you get that the Doppler effect in the first place conceptually occurs because velocity is relative, and if you look at your calculations and you see that every time you get a Doppler effect, and I'm talking about your calculations, our calculations, you wouldn't be able to see any of this if you just plug in numbers into the Doppler effect equation that's all over the web. Let me remind you again, there is a Doppler effect equation all over the web and all over Chegg. And you can download, you can use it, you can Google it, you can use it in your spare time if you want, but it will not help you on the final exam, because it will, even though if you use it very carefully and if you use it and memorize a lot of rules about where to use what plus sign and where to use what minus sign, you can get answers sometimes that equation, but you cannot see any of what I'm trying to say right here. It does not reveal any of the conceptual content of what's going on, which is one of many reasons I don't like it. But if you do it our way, if you solve Doppler effect problems the way we are trying to do in class, what you see is that mathematically you can only get Doppler effect answers by invoking the relative nature of velocity, right? Like you can only get the answers that we're talking about by actually saying VWR equals VWM plus VMR. And then you have to say, I don't know VMR, but I know it's the opposite of VRM, right? Like you literally have to use these equations to get the numbers. And then if you do that, here's what I'm trying to say. If you do that, you're reinforcing the relativity of velocity. So then it would be very, very easy and reasonable to infer from that, oh, right, relativity of velocities. Me to you is just the opposite of you to me. Like I'm going 65,000 miles an hour to the west past the sun, but I could just as easily and correctly say that the sun is going 65,000 miles an hour to the east past me, or I just said it backwards, but right, like right? So it would be very, here's where I have to slow down, because please try to follow this. It would be very natural and reasonable to then go, oh, source moving in toward receiver, receiver moving in toward source. As long as nobody changed the numbers, if we're talking about a source moving in toward a receiver at 40 meters per second, or a receiver moving into a source at 40 meters per second, like those should be equivalent scenarios according to relativity. Like one should think, and one would be right to think that. And so therefore, even if you are following everything we're doing, it would be very reasonable to be like, oh, okay, I get it. When the receiver moves into a source, there's a Doppler effect. So the receiver won't get a 440 hertz frequency. The receiver will get like a 492 hertz frequency. Okay. But then it would be reasonable to think, well, then if the source is moving toward the receiver, that's like the same thing, right? Receiver moving into source, source moving into receiver. And I could picture it at Coney Island, like either way, like you're smashing in toward those waves, like there's waves going from one thing to another, and the thing and the other are like smashing and coming closer to each other either way. So the waves will be more frequent. So it would be very natural to think whether the receiver is coming into the source or the source is coming to the receiver, that we should get not only qualitatively the same effect, but that we should get quantitatively the same effect. It would be reasonable to think that, but that's not what we're getting. We're getting a conceptually similar, I mean, we're getting a qualitatively similar, but quantitatively different effect. Let me even try to be more clear about it. And that is weird. That tells you something about something somewhere. It's not wrong, but you should see how it's in a way maybe unexpected or at least noteworthy. Let me try to be more clear if I can. Oh, well, yeah. All right. So first of all, what this is just putting in words what I just said, like explicitly note, like the whole phenomenon of it, of what we're calling a Doppler effect, but a lot of people call it the Doppler shift. I mean, same idea. I mean, same thing. And by shift, they mean that the the frequency that you receive is not the same as the frequency that you measured at the source. So people call that a shift. I mean, it's a little bit misleading, but but this whole phenomenon, whatever you call it, Doppler effect or Doppler shift, it occurs because velocities are relative. Yet, what I'm trying to tell you, what I'm trying to have you see in the numbers, if you've done them, is that motion of source relative to receiver doesn't give you the same effect as motion of receiver relative to source. That should give you pause. I'm not trying to confuse you, but I'm trying to say that if you really understand what we're saying, there's a moment in there that you should stop and realize, like, oh, wait, huh? Like it is kind of a thing. Um, so that's what I'm saying. Let me try to be even more concrete about that. Okay, just for compare and contrast here, imagine for the moment that I'm throwing baseballs at, like I'm not sending a wave at you, I'm throwing baseballs at you, a baseball or many baseballs, maybe many baseballs one after another. But imagine I'm throwing each a 15 meter per second pitch, meaning each baseball I throw is like leaves my hand at 15 meters per second relative to my hand, right? Because like that's what I could control with a baseball. It's like what my hand does, right? And that's very high, by the way. I mean, it's a little bit. I mean, it's definitely unrealistically high for me. Like I can't do that. In fact, it's a little bit higher than even a professional baseball player would throw, but not much higher. And it's a nice round number. So just like imagine that, right? Here's the part, the key part to imagine. Okay, so imagine I'm throwing baseballs at you. You know, each pitch is like a 15 meter per second pitch. Okay, now if you start running toward me at 4 meters per second relative to me while I'm doing this, and I'm asking you to picture this. I mean, you might want to write things down to work out the numbers. But like, if I throw a pitch at you at 50 meters per second, and you're just standing there, then okay, you'll receive a 50 meter per second throw. You'll catch a 50 meter per second throw. If you're running toward me while I throw that, if you're running toward me at 4 meters per second, I'm not trying to trick you. I hope maybe I should ask in the chat, but I will say, I think that you won't receive, like relative to you, then you won't get a 50 meter per second pitch. You'll get a 54 meter per second pitch, right? Like if I'm throwing it at 50, but then you're running in toward it, so it's going 50 relative to me, and you're going 4 relative to me, but you're going in the opposite direction. I hope, or I think you'd agree, and we could write it out, but I think to you, the ball will come in at 54. I mean, maybe I should pause on that. But right, I mean, it's 50 minus 4 technically, but also just intuitively, like if you're running in toward the ball, like it's coming in at you faster than if you were just standing there waiting for it. And how much faster? Well, 4, because you're running at 4, right? So, well, I'll write it. Okay, hopefully could maybe somebody in the chat just tell me, does that make sense? Oh, cool. I was just about to ask. Okay, wait. Hold on a second. Right, cool. Thank you, private chat person. Yes, just to clarify what I'm doing right now. So someone just wrote in the private chat, just to clarify, am I explaining the effect of the person catching the ball and how their motion has an effect? Yes, I am. That is what I'm explaining. And I'm doing it. And I'm glad you asked. And I was just about to make sure that people were still with me. Right now, I'm making an analogy I'm talking about baseballs or whatever to show how something funny is going on with waves. So yes, right now I'm saying if I'm just throwing 50 meter per second pitches, right, which is like 120 mile an hour pitches, which is kind of fast, but I'm throwing 50 meter per second pitches towards you. And I'm saying, and if you just stood there, then you would catch 50 meter per second pitches. If you start running toward them at 4 meters per second, you're going to catch 54 meter per second pitches. And I don't mean that to be a surprise to them. I mean, hopefully people, that's supposed to be straightforward. Like, I think you would all agree with that if I just asked you that out of nowhere, right? But so yes, to private chat person, good. But now what I also want to say, and also this is not meant to be a surprise, but this is all meant to be a contrast or like a base case so we can understand the wave thing better. I also want to say that, next page, similarly, if I run toward you while we're doing this, and if I run toward you at 4 meters per second relative to you, what I want to say here, again, this isn't itself is not meant to be a surprise, really. This is itself just the relative nature of velocities again. But I want to say, if I were, so I'm throwing these baseballs at you 50 meters per second. If you're running in toward them at 4, but they were going at 50, you'll catch them. They'll be hitting your hand going 54. In other words, they're going to hurt more. If I'm running toward you at 4 while I throw them, they're going to hurt more than if I were just standing there. How much more? Well, 4 meters per second worth more. I mean, then the kinetic energy will be like 1/2 mv squared, so it'll be squared. And like, I don't know literally how that translates to pain, but they'll be going 4 meters per second faster when you catch them if you were running toward me while I threw them. But the thing is, if instead I'm running toward you, that's going to have the exact same effect. And right, like whether you're running toward me or I'm running toward you, as long as all the numbers are the same, the effect will be the same because velocity is relative. If you're running toward me at 4 meters per second while I'm throwing these 50 meter per second pitches, you'll catch them or they'll hit you at going 54 relative to you. But similarly, or literally identically, equivalently, if instead of you running toward me, if I'm running toward you while I throw them, if I'm running toward you at 4 while I throw 50 meter per second pitches, it's almost easier to picture, I suppose. Like I'm throwing a 50 meter per second pitch, but then I'm also running at 4. So even though the pitch comes out of me at 50 meters per second relative to me, I am coming toward you at 4. So VAB plus VBC equals VAC. The pitch will hit you going 54. What I'm trying to say to everybody is, if it's a baseball, me to you, you to me, no difference. If one of us is coming in at 4, that 4 is going to get added on to the velocity of the baseball. And instead of receiving a 50 mile an hour pitch, you're going to receive a 54 meter per second pitch. Whether you're moving to me or I'm moving to you makes no difference because that is the relativity of velocity, right? I'm not saying, like, I don't even know if that's a surprise or not, but that's not meant to be a surprise. That's meant to be just the fact about velocity. If you run toward the pitches or the pitches run toward you, same effect either way. Again, it's just like saying whether the earth is moving past me or I'm moving past the earth, whether the earth is moving past me or I'm moving past the earth, same thing. Velocity is relative, right? Same thing with baseballs. But what I'm trying to say is with the Doppler effect, that's even though we're totally using the relativity of velocities, with the Doppler effect, if you look at these numbers, if you practice what I'm saying and run the numbers, you'll see that actually this doesn't seem to hold up. because when the receiver comes toward the source at 40 meters per second, we get a received frequency of like 493 hertz. But when the source comes toward the receiver at 40 meters per second, and again, holding everything else the same, there's no trick here. If the source comes in, then you don't get 493. You get like 499 or 500, a different number. Is there anybody that, so that's different. Like something is, even though we're totally using the relativity of velocities to run and analyze and believe in this Doppler effect, something about the relativity of velocities seems to be falling apart or acting funny here. If you're, let me see. So there's something in the chat, which is good, because I definitely need to know if you guys are following this or not. Like so someone is weighing in, which I'm going to read, but that they don't need to be the only person. Hold on. Let's see. Yeah, right. Okay. So in the private chat, someone is saying, I'm not going to read the person's name, but I'm literally going to read it because it's like the right question. Someone's saying in the private chat, they're saying, so does a pitcher throw faster when in motion rather than pitching while standing still? Yes, that is what I am saying. And I'm ultimately, part of what I'm saying is that's as opposed to waves. Like, yes, a pitcher and a baseball have that relationship, but a speaker and a sound wave do not. Even though velocity is still velocity is velocity, like whatever it is for everybody. So let me just read that again, because yeah, that's what I'm saying. She or he says, Elijah says, that's a joke, it's a bad joke. It doesn't even make any sense. Okay. Vladislav Richter says, does a pitcher throw faster when in motion rather than pitching while standing still? Let me actually be like the answer to intuitively what they're asking is yes. Like I believe I know what the person in private chat's asking. I believe the answer is yes, but let me actually be very careful about the words now. Like what I'm saying is a pitcher throws what a pitcher throws. I mean, a pitcher or a person throws a ball at a certain speed relative to the person. Let me back up even one more step, actually, because yeah, I mean, this is the point I'm trying to make. Like, first and foremost, I'm saying velocities are relative, right? Nothing in the world has a velocity. That's a big lesson. Like, that's actually the nugget of physics 203 is that, but the reason is it never goes away. This is the nugget of physics all the way through Einstein, through the 20th century, even when the math and everything gets super complicated and fascinating and fabulous. At the core of all of this, what we have is the recognition that nothing in the world has a velocity. Things only have velocities in relation to other things. And that lesson is so big. Like honestly, every new chapter in physics is a new implication of that lesson. And on the one hand, what I hope is that you all get that is a lesson. Like one hand, hope that you all are like, oh yeah, I've seen that. He said that before. I get that. But I also hope that you all also are getting that each time any of us, any physicist, anybody thinks that they get that, it turns out there's another implication of that shows us that we even thought we got it, but we didn't realize really how true it really is. Like, it's not just true in the cases that seem reasonable and obvious, it's true in the cases that don't seem reasonable and obvious. So what I'm saying is this: everything has a velocity in relation to another thing. When I throw a baseball, what I can control is the velocity of the baseball relative to me in the case of a baseball. Like if I throw harder, then the ball leaves my hand faster than it otherwise would. What the baseball is doing in relation to anything else in the universe has as much to do with everything else in the universe as it does to do with the baseball. So yes, if I throw a 50-mile-an-hour pitch, no matter what I do, I have this muscle, I do this coordinated thing or this uncoordinated thing, and now the baseball leaves my hand at 50 miles an hour relative to my hand. If I stand on the pitcher's mound and you're standing on home plate or like whatever, we're both standing on the ground and I throw that 50-mile-an-hour pitch relative to me, well, then 50 miles an hour relative to me plus 0 of me relative to the ground makes 50 miles an hour relative to the ground. So if you're standing on the ground, you get a 50-mile-an-hour pitch. Now, if I'm running while I throw it, it's still 50 meters per second, 50 miles an hour relative to me. I can't change that. I'm not changing that. And it'll still like every hour, it will still be 50 miles ahead of me if it kept going and going, right? I'm not changing that. But if I'm running past the ground while I do this, then that means every hour it's 50 miles ahead of me. But if I'm running at 4 miles an hour relative to the ground, then every hour I'm 4 miles ahead of where I was on the ground. So compared to the ground, the baseball will go 54 rather than 50. And if you're standing on the ground, yeah. So if I'm running toward you, you'll get a faster pitch than you otherwise would have. Or if I throw it out of a car and the car is going toward you, then that will speed up the pitch relative to you, not relative to me, but relative to you. And they're both correct, right? It'll still be a 50 mile an hour pitch to me, but it'll be a 50 mile an hour, 54 mile an hour pitch to you. And when I say they're both correct, or when I say that both numbers are true, part of what I mean by that is I can't catch up to the baseball just by going faster, right? Like I could throw a 50 mile an hour pitch off a train, but even if the train's going 100, I don't overtake the baseball, right? The baseball just stays 50 miles an hour ahead of me. So if the train is going 100, that just means now the baseball is going 150 relative to you people on the tracks or on the ground. I can't catch up to that baseball because the baseball goes away from me at a certain speed. So the answer to the private chat question is, yeah, baseballs do that, but waves. So two things but waves don't do that. If I throw a wave out of me, if I shout a sound, and the sound goes out at 340 meters per second, it doesn't go 340 meters per second relative to me. It goes 340 meters per second relative to the air that it's traveling through. That is still relativity of velocities. We're still saying nothing has its own velocity. It's always compared to something. But in the case of a wave, the comparison is to the medium. In the case of a particle, there is no medium to compare it to, right? This is fundamentally different. So number one, I could shout and I could run fast enough to catch up to my own shout. That is part, I mean, I know I said this part 3 weeks ago, but that is what I'm trying to drum in. I mean, this is what is so crazy about waves. They totally obey the relativity of velocities, which is already an interesting thing. But waves have a built-in thing called a medium, and the relativity of velocity applies to their medium. Baseballs don't have a medium. So first of all, conceptually, what I've been trying to say is literally if I shout and the sound comes out of my mouth at 340 meters per second relative to air, if I then jam on the accelerator, like if I shout it out of an airplane and I start driving up, I go faster and faster and start flying at a rate of 340 meters per second relative to air, which is possible, then I would literally catch up to my own sound. You can't do that with a baseball, but you can do it with a sound because there's this thing called a medium for the sound that makes all the difference, right? That's like first conceptual point I'm trying to make. But then how it pans out numerically, how we see this in our calculations here is to bring this all back. Then I'm saying with a baseball, whether I run to you or you run to me, no difference. Either way, it's going to speed up the baseball. Whether the source is sped up or the receiver is sped up, either way, that's going to speed up the baseball relative to the receiver and by the exact same amount. If I throw a 50 meter per second pitch out of my hand, if I run toward you at 4 meters per second while I do that, or you run toward me at 4 meters per second, you're going to get that baseball. You're going to receive that baseball going 54 meters per second relative to you. And in fact, let me go one step further. Let's say it's not just one baseball, but let's say I'm throwing one baseball a second, like continuously, repeatedly as I run toward you. If I throw, and this is ultimately really the thing I'm trying to say here with Doppler effect, if you try to sort of make a Doppler effect scenario, but out of particles, so I'm throwing baseballs over and over to you, or I'm shooting bullets, BBs out of a gun, like over and over, like a machine gun type thing, over and over. If I'm running toward you, if I'm not running toward you, if I'm just standing there and like one bullet comes out of my gun every second, then if we're all just standing around, then you're going to receive one bullet every second. I mean, if I'm shooting one bullet every second, and no one's doing anything interesting, then you're going to receive 1 bullet every second. If I start running toward you, hopefully you can picture you're going to receive those bullets more frequently than if we were just standing around. Like that's like the Doppler effect, right? If I'm shooting BBs, like 1 every second, but I'm running toward you while I do that, they're going to hit you more frequently than if I were just standing still. Hopefully you can picture that. Or similarly, if you're running toward me while I'm shooting 1 every second, they're going to hit you more frequently than they're being sent out. Not a contradiction, not a shock. I mean, maybe interesting, but the case, right? Because motion is relative. But here's what I'm saying: if they're particles, whether I run toward you or you run toward me, yes, either way, you'll get them more frequently than if we weren't running toward each other. You'll get them more frequently than if we were all standing still. But how much more frequently? Well, it's going to be the exact same, whether you're running toward me or I'm running toward you. It will make no difference, because me to you is just the opposite because of this thing, number 2 right here. Like, because of this, A to B is the same as negative B to A. Like, me going 5 miles an hour to the east past you is the same as you going 5 miles an hour to the west past me, right? So if I'm shooting BBs at you 1 every second, if I want you to get hit more frequently than 1 every second, I could run toward you, or you could run toward me. And either way will have the exact same conceptual and quantitative effect on that frequency. Either way, whether you run toward me or I run toward you, it's the same either way if we were shooting BBs. But if we're shooting waves, what apparently we're seeing here is if the source approaches, that's one case. If the receiver approaches, that's a different case. And they both will get an increased frequency, but not increased by the same amount. Something different is going on. That's what I'm trying to say. I mean, I know there's 16 minutes now, but like there's a million different ways we could ask questions about this, but I need you to see it. That like the first thing you need to be able to do is just solve the different 4 Doppler effect cases. And you'll see that in 2 cases, the frequency received is higher than the source frequency. And in 2 cases, the received frequency is lower than the source frequency. But then I also need you to see that it's not 2 pairs of identical answers. It's 4 distinct answers. And I need you to see that if you step back and think about that, that's not the way it would go with particles. Like, in fact, well, yeah, it's not the way it would go with particles. I need you to see that. I need you to know what you would expect if it were particles. What you would expect is all of what I was just yelling about baseballs. Like with particles, receiver coming in or source coming in, what's the difference? Velocity is relative. But with waves, receiver coming in or source coming in, apparently there is a subtle difference. Now with 15 minutes left, and again, please put in the chat if you're following me or not. This might be all getting very abstract and like conceptual. So let me go back to the numbers and show you what I mean. Again, in the numbers, well, right, remember, okay, so these were the numbers. I mean, we've done this case, like, I mean, we've done these numbers like a million times now. And again, and by the way, again, on the final exam, that 40 is not going to be a 40. It's definitely going to be substantially higher just to make all these distinctions that much more vivid and dramatic. But if you take these 4 basic numbers that we keep churning through, what I want you to see is that what we did slowly together in class is we computed FWR. Then very quickly, I mean, that's what we always compute FWR, the received frequency. Well, I did it slowly in class for where VSM was 0 and VRM was -40. Then I quickly at the end of, then I asked you to do the other case, and I quickly at the end of class like blasted through with these numbers, and we got a slightly different result. Please look. Okay, I'm gonna walk through now what happened when we got these 2 different results. And please look at your notes. I'm almost intentionally not going to turn the page. Look in your notes for how you did it or how we did it, how I did it, and you'll see the same procedure for both ways. It's the same procedure for solving, but yet somehow the numbers ended up being different. And I want to point to where they were different. If you look, if you look. And I'm going to just say this, so please stop me if it doesn't make sense. If you look first at the received, if you look at the case where the receiver is approaching, right? First you solve, as you always do, first you solve for the wavelength according to the source. And what you did, if you did it right, when you got the wavelength according to the source, if you really break down what you did, you'll see you did in effect 340 plus 0 over 440. And you got something like 0.772 meters. Let me say that again slowly. Step one of the procedure always is solve for the wavelength according to the source. And how do we always do that? We say wavelength is velocity over frequency. And how do we get the velocity? Always we break it into two steps. We always say, in this case, for example, we said velocity of wave according to receiver, in other words, VWR, which is what we needed. We said, we broke that down to two steps and said VWR equals VWM plus VMR, right? And we said, oh, in the original case where the receiver was moving in, when the receiver was moving in at -40, that meant VR. And please, again, look at your notes and see if I'm not crazy. Like, I would point again the page, but I feel like I've done this page so many times, it's just going to turn everybody off. So like, see if you see what I'm talking about, that when we're doing the receiver approach case, when we did the receiver approach case, we were given that VRM equals -40, right? So then when we were solving for the wavelength according to the source, we needed VWS over FWS. VWS, meaning velocity of wave according to source. We didn't know that. We weren't given that. We were given the velocity of the wave relative to the medium, 340. So we said VWS equals VWM plus VMS. And then we said VMS, what does that mean? Oh, we don't know, but it's the opposite of VSM. And in this case, VSM was 0, like the source was just sitting there when we did the receiver moving case, right? So what we did in the first step is ultimately we said 340 plus 0 over 440 hertz equals 0.772 meters. We found that that's the wavelength according to the source. Then we said, oh, well, the wavelength according to the source and the receiver always have to be the same. So we went over to the receiver side and we said, okay, we've got a wavelength now according to the receiver. Let's just do this same thing in reverse. Let's use this wavelength to get the frequency. So we went over to the receiver and we said, okay, frequency of wave according to receiver is velocity of wave according to receiver divided by wavelength of wave according to receiver. We, in other words, said VWR over over lambda WR is what we need. And then we said, oh, we don't know VWR. We don't know the velocity of the wave according to the receiver. What we know is the velocity. So we'll have to say instead of VWR, we're saying VWR equals VWM plus VMR. And then we said, oh, well, we don't even know VMR as such, but we were given VRM as -40, right? As -40. Let's go. Oh, right. Oh, yeah. Right. We were given Elijah, that was totally your fault. Sorry. No, we were given VRM as -40. So we said, aha, VRM is -40, but we need here, according to this equation, VMR. So we said VMR must be +40. In other words, if the receiver is moving in through the air at -40, then the air is coming back at the receiver at +40, right? So we said, aha, for our final answer for the frequency of the wave according to receiver, we did FWR equals 340 plus 40 all over that wavelength that we just saw for 0.772. So we said, aha, frequency, final frequency that we're solving for is like 380 over 0.772. And again, you might have chopped off digits at a slightly different place. You might get a slightly different number, but we basically got 380 over 0.772, and that yielded something like 493 hertz. Okay, that was in the case when the receiver was coming in toward the source. In other words, if we back off that, what we found is we had a normal, everyday, unaffected, uninteresting wavelength that was coming in from the source to the receiver, but the receiver was running in to meet that normal, everyday wavelength, and therefore met it more frequently than we might have expected or than the source expected. And so we get a frequency that's higher than 440. We got like 493. But now, contrast that to if you do the exact same procedure, if you follow the logic and do the same procedure, but apply it to when the source is moving, even though the source is moving also at that number 40. And even though it all looks like the same thing, like we were just doing this, but now we're going to do this. And that seems like if it were somebody throwing a baseball and somebody catching a baseball, like what difference would that make? If we break it down and actually look at our calculations, and we don't just plug and chug in randomly into the thing on the web, because that wouldn't reveal any of this. If we look at our calculations, then in this case, what happened was right from the get-go, when we solve for the wavelength, and I'm looking at the time, I know we have 7 minutes, so this is just perfect to do this. But really, I hope people are following. I mean, we're spending so much time on this. I really hope we're getting something out of this, or that you're stopping me if I've lost you. But if we now look at this other case where the source is moving toward the receiver, we follow the same procedure. The procedure says first, get the wavelength according to the source. Do velocity over frequency. Okay, we want velocity of wave according to source over frequency of wave according to source. So we say to ourselves again, oh, we don't know the velocity of the wave according to the source. All we were given is the velocity of the wave according to the medium and the velocity of the medium according to the source. If the source is moving now, we say, aha, we were given that the source was moving into the medium at positive 40, because it's going the same direction as the wave. It's going in, right? So positive 40, that's VSM, the velocity of the source relative to the medium is positive 40. The equation says what we want is VMS, right? Because VWM plus VMS equals VWS. So we do, in this case, we do 340 plus negative 40, right? The velocity of the source relative to the medium is positive 40. Therefore, we say the velocity of the medium, according to the source, is negative 40, i.e., from the standpoint of the speaker, there's like air coming in, there's like wind blowing at it, like in the opposite direction of the wave at negative 40. So we do 340 plus negative 40 all over 440 hertz. So in other words, 300 over 440 hertz. And we get a wavelength this time of 0.681 approximately meters, right? So no, right from the get-go then, what we're following the same procedure, but what we're now saying is, oh my God, wait a minute. The wavelength that's coming out of the source is no longer, is not 0.77 meters, as we would expect if the source were just sitting around sending out, playing a middle A on the piano, sending out a 440 hertz. Now we're saying, oh wait, this source is sending out what it thought was a 440 hertz, but it's running in towards it as it sends it out. So it's sending out these wave crests and running towards the crests as it sends them. So if you think about it, if it's like you send out a crest and you're going to send out a crest like 440 of them every second. So you send out a crest and then a 440th a second later, you're going to send out the next crest, but you've run in a little bit since you sent out the last one. So by the time your next crest comes out, it's closer to the last crest than it otherwise would be. So now all the crests are compressed. Like this is what textbooks would refer to as a compressed wavelength. We're now right from the get-go sending out a sound that it's still a 440 hertz pitch, but the wavelength of it is not set 0.77 as we would expect, but 0.68. The wavelengths are smaller now and they're traveling toward the receiver. And now, even though they're smaller than we would expect or smaller than the other case, still we solve for them because no matter what they are, the receiver and the source will have to agree. Like we're sending out a funny wavelength now, but but both the receiver and the source will totally agree on the funniness. The receiver is going to get a 0.68 wavelength sound. So when we go to that last step, now we're saying, okay, and I know there's 3 minutes left. Frequency according to receiver, i.e. FWR is going to equal VWR over lambda WR. And what is VWR? Well, we weren't given it explicitly in the problem. We don't know the velocity of the wave relative to the receiver, but we know that VWR is VWM plus VMR. And what is VMR in this case? Well, I don't know. I was only given VRM, but that was 0. So VMR is like negative of 0, which is 0. So now in this final calculation, we do 340 plus 0 over 0.68. In other words, with 3 minutes left, just purely mathematically looking at this, in one case, what we really had was 340 over 440 yields 0.77. And then we did 340, and then we did 380 over 0.77 and got a final answer. Here we're doing 340. Sorry, here we're doing 300 over 0.77. No, sorry, we're doing 300 over 440 and getting 0.68, and then plugging that in and doing 340 plus 0 over 0.68 and getting a different number. Like the numbers are different because the numbers are different. But conceptually, what we're saying is in one case, you send a regular everyday wavelength to a receiver that's running in to meet it. And in the other case, you sent out a shorter wavelength to somebody who's just standing waiting for it. It's physically two completely different things that just happened. They end up with conceptually a similar result, but quantitatively a different result because it is two different things. What am I really trying to say with 1 minute left? What I'm trying to say that I want you to follow is that no matter what, velocity is still relative. There's no such thing as my velocity. There's only my velocity relative to you. And it is still true, or to somebody else, or to somebody else. And it's still absolutely, with 40 seconds left, it is still absolutely true that my velocity to you had better always, 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 always be the exact opposite of your velocity relative to me. But the difference between baseballs and waves is this. If I throw a baseball to you, then it's all about me and you. My velocity to you is the equivalent of the opposite of your velocity relative to me. If I throw a wave to you, it's not about me and you. It's about me and the medium or you and the medium. The relative velocity still applies because my velocity relative to the medium is exactly the opposite of the medium's velocity relative to me. And your velocity relative to the medium is exactly the opposite of the medium's velocity relative to you. But you and I are not the relationship anymore. If I throw a baseball to you, it is about me and you. If I throw a wave to you, it is about me and the medium and you and the medium. That's the huge difference. And it's ultimately because of that we believe that the universe is expanding and we believe in a Big Bang. But I'll say more about that on Wednesday, and I'll give you the final exam Wednesday. And thank you very much again for being so attentive and understanding. And I will go to my next class. But I hope that's clear. I hope that's clear. Goodbye. Okay, I don't even know. Okay, thank you. No, I do appreciate it. Okay. Thank you. No, really. No, you, okay. Thank you. And yes, okay. And thank you also, Elijah. Okay.